Okay, I hope I am audible and screen is also visible. Please, can you confirm? Am I audible?
Yes, sir.
No, thanks. Okay, so this is um, this is tutorial 10. Tutorial 10. Algebra. This is 03 and today is 29th March. Okay, so before going to the inner product space, all these things, uh, I'll just discuss some problem. Let's start from here. Okay, so this is a problem of NET exam, hopefully 23, which is some 23, some of the, actually I can't remember the properly um, um, which session it was, but it was a it was there. Okay, so this is regarding the Jordan canonical form, which is already done. So let's try to do that this problem. Here is the question is that uh, suppose a 7 by 7 block diagonal complex matrix A has blocks 0, 1, 0, 1, 0, 0, and 2 pi I, 1, 0, 2 pi I along the diagonal, and which of the following statements are correct, are true. So clearly here all blocks are distinct, but you can look at corresponding to 0 eigenvalue, there is two block. One is of corresponding, uh, yes, what, anything you are
Yeah,
saying?
option one is correct.
Okay, option one is, I don't know whether option one is correct or not, but yeah, I'm just, I'll also try here. I have not checked it. Just take some quick problem and, okay, just a minute. I'll check here. Maybe you was correct, but I don't know. Yeah, option one is correct and it's four is correct, but let's check. Okay. So which of the following statement is or are true? So clearly the matrix will be clearly the you can look at the um, here corresponding to zero eigenvalue. One block is of 1 by 1 and one block is of 2 by 2. So clearly the minimal polynomial of this particular matrix will be corresponding to 0. It will be 2 minimal polynomial, and so and and you can look at corresponding to 1 there is one block, so therefore I will write at least one, and other is the corresponding to 2 pi I. Here you can look at there is corresponding to 2 pi I, there is two block. Okay, so two block is one is of 2 by 2 and one is of 1 by 1. Okay, this is not three block. You can look at this is three block, but this is actually in Jordan canonical form, this is two
Yes,
different
sir.
block.
X minus 2 pi I whole square, sir.
Right. So x minus 2 pi I whole square. 2 pi I whole square. So this is the minimal polynomial. This is
Yes.
minimal polynomial. So characteristics polynomial you can look at the corresponding. So therefore, characteristics polynomial is maybe minimal polynomial is not needed, but we are just calculating because there is the question whether minimal polynomial is this or not. So you can look at the corresponding to 0. There is three total 0 eigenvalues. So characteristics polynomial is actually the I mean
Like
appearance of
cube.
the eigenvalue. Yeah, appearance of the eigenvalue. So this will be 3, and other is corresponding to 1. There is one only block and there is no appearance. And so corresponding to 2 pi I, there is 3 times appearance of 2 pi I. So x minus 2 pi I whole to the power 3. So characteristics polynomial is this. This is correct. Minimal polynomial is not correct because this is square it is, but it is not correct. Dimension of the eigenspace of 0, 1, 2 pi I. Okay. So eigenspace of, so geometric multiplicity or the dimension of,
2 1 2.
yeah, corresponding to 0, that is 2 because there is 2 block in
Number,
the
yes, sir.
canonical
No,
form.
this
And geometric multiplicity of 1, that will be
1
1, and geometric multiplicity of
2
2 pi
2 pi,
I,
yes.
that will be 2 because there is the appearance of twice appearance. So this option is also not correct because here it is saying that corresponding to 2, here it is saying 3. That's why it is not correct. The fourth one is the dimension of the eigenspace of 0, 1, 2 pi I is 2, 1, 2. That's correct. So this is correct. So this is the question. Okay. So obviously this seems easy, but every time, I mean, not there must be some one or two options which is something you can't discard, you can't even make them as a choice of your questions. That happens sometimes. So be careful for this type of situation. So let's try another problem. I have collected 3 4 problem for not
Sir, I
more
think
than
it
that.
is net problem, sir. I think.
Yeah, these are net problem. I'm collecting net problem because
Yes.
other guy is
Part
also
C, sir.
doing other guy is also doing the same thing, but problem is that I don't have that much time to collect questions, and I am also not that much right now. I'm not that much of questions and where to find questions, solutions, and all those things. But I have just tried to find 3 4 problem of linear algebra because I have to collect those problems which are from there, because quadratic form is still not done yet, but there are
Yes,
some
sir. Yes.
problems which are coming from the quadratic form. So that's why I have to select questions which are
Yes.
not involving analysis but only linear algebra, purely linear algebra. I have to do collect those problems. So I don't have that
Yes, sir.
much time. So I have collected 3 4 problems. So let's do this problem. What it is saying that let T be a linear operator from R5 to R5. This is R linear transformation. That means linear operator over the vector space R to the power 5, and field is R here. And suppose that this 5 vector, let's write those vectors alpha 1, 1, minus 1, 2, 4, 0, and beta 1, that is equals to 4, 6, 1, sorry, not alpha 2. I'm writing alpha 2, 4, 6, 1, 6, 0, and alpha 3 is equals to 5, 5, 3, 9, 0. These are the 3 vectors span the null space of T. Which of the following statement is or are true? So, so span linear span of alpha 1, alpha 2, alpha 3 is actually the null space of T. So now you can look at here we have 3 vectors, but that does not imply that the null space of T has dimension 3, because we may have that one vector is linear combination of other two. So in that situation, dimension is not necessarily 3. So we have to check whether these 3 vectors are linearly independent or not. If these 3 vectors are linearly independent, then we can directly say that the dimension of the null space of T is 3. So we have to check it. Okay. I think this is also, as we have R, so this is also
They are
4.5, 4.
linearly, sir, they are
Yes.
linearly independent, sir. Linearly independent, sir.
So, but you have to check, no? I mean, that maybe they are linearly independent because this
Form a
option,
matrix by, sir,
yeah,
considering.
we have to form a matrix and check its I mean, do the row reduction type of process. So let's go to the formality. So you can do it quickly, as quick as you can do in consider the matrix. This is maybe I'm writing correctly. 1 minus 1,
Sir, what
2.
is option 2, sir?
Option 2 is suppose that for every vector v there exists an n such that t to the power n equals to 0, then t square must be 0.
Okay, sir.
So option is 4, 6, 1, 6, 0. So option C, B is something like statement is same with the option C, only t to the power 3 in place of t to the power 3 it is written t square. Okay. So
Yes,
5,
sir.
5, 3, 9, 0. So you have to check this is whether this is rank 3 or not. That is what we have to check. So let's do the row reduction process. That is obviously R4 dash is equals to R4 minus 4 R1, and R5 dash is equals to R5 minus 5 R1. So what we'll get, first write what it is, first one, and second one is 0, 6 minus 4, 10, 1 minus, okay, I have multiplied 2, minus 4 to 8. So this is minus 7, if I'm not wrong.
Minus
So
7 minus 10 0. Minus 10
that
0.
is 4, minus 10, 0. And next one
0.
is 0,
0
obviously,
10 minus
and
7 minus 11 0.
minus 10, minus 7, minus 11, right?
0.
0.
Yes, sir.
So
0.
this is the thing. Yeah, this is correct. So therefore, you can do the next one, that just to subtract from one another, you will get, this is one. Obviously, from here you can directly say that they are all are. This is, I'm writing this one as it is, and I'm just subtracting it from here. So this will be minus 1, 0. So therefore, we have three linearly independent row, as above we can see, as above matrix, as in the above matrix we can see, as in the above matrix we can see that we have only three non-zero, only not only, we have exactly three non-zero, because there is no only, exactly three non-zero or linearly independent row, linearly independent row. Therefore, the nullity of T is equals to 3, and that implies, via the rank nullity theorem, that the rank of T is equals to 2, because the dimension of the vector space is 5. So rank of T is equal to 2, that it is correct. Okay. So now second option. See what it is say, that suppose that for every vector v there exists n such that t to the power nv equals to 0, then t square must be 0. Okay. What we have seen is that these three vector will be there, right? As a these three vector will be there as a, what is called, okay, what we can see here is that here, as it is saying, suppose that for every vector v there exists n such that t to the power nv equals to 0. Okay, so t to the power nv equals to 0, that implies that none of the vector is eigenvalue. So there is no eigenvalue except 0. 0 is possible eigenvalue. I am not 0 is also eigenvalue, because you know that whenever t to the power nv equals to 0, so one can write t to the power n minus t to the power t to p into t to the power n minus 1 v is equals to 0 if t to the power n minus v is non-zero. So I mean, it is either t is completely zero operator, but that is not the case, because we have rank is 2, because null space is something fixed, that is 3. So t is a non-zero linear operator. First fact is this. Second fact is that if this is true for every vector v belongs to r to the power 5, there exists an n such that t to the power nv equals to 0. So therefore, what we can say is that there exists a vector v which is non-zero, and t to the power tv is equals to non-zero also. I can say that one. Tv is also non-zero, and I mean, for every vector v belongs to r to the power 5, there exists an n such that t to the power nv equals to 0. Then obviously there must exist a vector v for which this n will be at least 1. N will be at least 1, because n can't be 0. Because if n is 0, that means for every vector tv is equals to 0. That is not the case. So that means there is 0 is an eigenvalue. That is clear. And that is clear from here also. You don't need to go any place. But yeah, so the fact is that, but it is also saying that for every vector v t to the power n v equals to 0, that means none of the, no other eigenvalue is there. So 0 is the only eigenvalue there. If we can write, if for every vector if for every v belongs to the r to the power 5, there exists an n such that t to the power nv is equals to 0, that implies that 0 is the only eigenvalue of t, because there can't be any other eigenvalue. Why? Because if there exists any other eigenvalue, for example, let's take v dash alpha is an eigenvalue. That means that corresponding to some lambda alpha and lambda not equals to 0, I'm taking. Then t to the power n,
It
how
can
much?
never be zero.
Right, it will never be 0. So that's why there is no other eigenvalue. So that means that implies characteristics polynomial of t is x
It's
to the
to
power
power
5.
five.
5.
Yes.
So that implies minimal polynomial of t is something x to the power k, right? But we have to find what is the k.
Yes, sir.
Ah. So now you can, I mean, you have to use some trick here. Okay,
Cube,
so
it will be sir x cube because geometric multiplicity is 3.
that is the case, but why x2 is not the case?
Sir, so minimal polynomial is because it's cube, na sir.
Yes, if we say the minimal polynomial is, I mean, here geometric multiplicities. Why geometric multiplicities?
Yes, sir. We cannot say.
We can't say anything here.
We only say when it appears in geometry, Jordan canonical form 3 times.
But yeah, that will also will work. Zero is okay. You can look at zero is an eigenvalue, and three eigenvector is there clearly, right? So
Ah.
geometric
Yes, sir.
corresponding
That is true, sir. Yes, geometric multiplicity is
of
this
zero is
dimension of,
right. So
yeah.
that means what will be the Jordan canonical form of the, then note that, or note that Jordan canonical form
So there will
of
be,
T is either do two case, only two case will be there, because we have geometric multiplicity 3. So I
sir,
think
only
there is
one case. There is
only
only
one
one.
case, right? T is only one case. That's true. Exactly. This is only one case. That is 0, 1, 0, 0, 0, 1, 0, 0, 0. This is one block, and we will have other two block, and that is only two option is there, 0, 0.
True.
We have to write this one as geometric multiplicity of 0. Geometric multiplicity of 0 is 3. Then Jordan canonical form is there. So that gives that t to t cube equals to 0, because you know this matrix will be 0 if you do 3 times. Because if you do this type of matrix is very interesting matrix. If you square it,
Yes.
you will get 0, 0, 1. I mean, this is something like
Yes, sir.
pushing one, and after that, if you multiply this one
Yes,
with
sir.
again
Then
this one, this will again
yes.
then vanish.
Those entry
Otherwise,
will go upper side.
yes. So t cube equals to 0. So therefore, obviously 2 is then false, and 3 is true, right? Now next is that, okay, this is something work. Okay, I have to show that whether this is in linear combination or not.
Yeah, this is sir simple, sir.
So I'm leaving it. I don't know. I'm leaving it because this there is nothing to do. Just you have to check what is in. Okay, check it. So obviously two option is correct, and so fourth option is correct or not. That depends on the. I mean, you have to do some work. That's, you have to spend time. That is all.
Sir,
So
here the sir main point is sir when you said that the zero is the eigenvalue, sir. This is the main
0 is
point,
the
sir.
only eigenvalue, because here it is. This is the, I mean,
Ah,
for
sorry.
these two factors, 0 is the only eigenvector,
Yes, sir.
eigenvalue, because this is what, because you have said that one other can't be eigenvalue, but actually thing is that problems in net are not tough. You have to find the correct statement, then you will do it easily, quickly. Obviously, when you do
Yes, sir.
in exam, you should not do it very. I mean, you should not do with full formality whatever I am doing. Obviously, we will not do.
Yes, sir.
Okay. So go to another problem. I think all of these problem are 23. Actually, I have only opened 23 paper and take the questions from there. Okay, what it is said that A is given the matrix 1, 4, 2, 3, and so therefore characteristics polynomial of A is x 1 minus x no, 1 minus x.
X
Determinant
square
of 1
minus
minus
7
x,
plus
4, 2, 3 minus x. That is equals to 0.
2
So
minus
this will
5.
give that 3 minus 4x plus x square minus 8 equals to 0. This will give that x square minus 4x minus 5 equals to 0. So therefore, by Cayley-Hamilton theorem, A will satisfy its characteristics polynomial. A will satisfy characteristics polynomial that is a square plus minus 4a minus 5 equals to 0. Okay, so we have this, and here question is that this is the given condition. This is also, as it is written, which of the statement are correct. So this is also 4.75. Okay, I have to write that statement a to the power. Okay, just a minute. I have to write that one correctly. A to the power 5 minus 4a4, I think. That is minus 7a3 plus 11a square minus a minus 10 identity, that is equals to giving us a that is equals to a plus b identity. Then what about the a and b something else. So let's first do find what is a and b, because this is clearly possible to find. So let's take common a3. So it will be a square minus 4a minus, I will take only 5 identity. So therefore we will have minus 2a cube plus 11a square. So I am removing this one because this is consider this. So therefore we will write this one minus a minus 10 times identity. So this is 0. So therefore this full thing will be 0. So let's take minus 2a common. So what we will have, a square, I will forcefully write for a minus 5. So whatever I have here, minus plus 8a is added. So minus 8a square will be plus 10a is added,
Minus
minus 10a. Yeah, minus 2. Okay, 2. Why 2a cube is there? Okay, sorry, sir. Okay, no, no, this is
minus
correct.
8
This
is
is correct. This is correct. Huh?
yes, sir.
I'm writing correctly, right? 2a cube is not there. So because 2a is adjusted,
There is
minus a square.
11 a square, sir, already,
Yeah,
na, sir.
yeah, yeah. I'll put at later adjust. So this is again 0. So this will be 3a square minus 11a minus 10 identity. So again take 3 common, a square minus forcefully write 4a 5 plus 12 is there, so plus a, right?
Hmm. Yes, sir.
Yeah, plus a and 15. So this is 4a, 4 identity, right?
Hmm.
15, yeah, 4 identity. So therefore this is equals to a plus 4 identity. I think it was written ai plus
But there is
bi.
10 I,
Yes,
sir.
huh? 10i
Sir,
na, 10i.
you
So
you should
we have
write 5 I, na, sir.
5i, sorry.
Plus
So
5. Last.
huh,
In last, sir,
minus,
sir,
yes,
you have written 4 I. It should be 5 I, na? Because we need 10 I, sir.
right, 10i, yeah. So a is equals to 1,
Rates of 5 I, sir. Last, yes. Page 1, B is 5.
b is 5. So what are the options? So let's write a equals to 1, b equals to 5. So this is not correct, obviously. Okay, a plus b obviously
Written
less
this.
than 7, that's true. A plus b is
Correct.
divisible by 2, that is correct. And a greater than 2, that is not correct.
Yes.
So this is done. Mm, What we have done, I think we have only limited this, we have done this, we have done this, we have done this is and this. Only these two problems are there. So let's try this one. I don't know. Sorry. Let's try this one. What it is says, we
Sir,
denote
first,
I. First one, which one is okay? I have to let me read it. We denote IN with the n cross n identity matrix. Which one of the following statement is true?
first is not correct, sir.
First is not correct. If A is real 3 by 2 matrix, B is real 2 by 3 matrix, such that BA equals to
Sir, because
identity,
rank is
then
less
obviously
than
this
or
is
equal
not
to
correct. I
our
think you
rank
can
of
create.
B.
I think you can only one can create counter example here, right? Because it is. I mean, not counter. Theoretically also one can say, because whenever BA equals to identity, that means A is injective but not surjective,
Yes,
right?
sir.
So if A is not surjective and B is surjective but not injective, but here it is saying something that B is, I mean, it is saying that it's saying reverse. Obviously, it will not happen. It will obviously not happen. Okay. So let A be a real matrix 3, 3, 1, 2. Then there is a matrix B with integer. Okay, with integer entry such that A B equals to identity. A be a real matrix. Then there is a matrix B with integer entry such that A B equals to identity. Okay, whether it will have inverse or not, that is the thing, right?
Yes, sir.
A very real matrix. So let's
So
check it.
it
The
have
determinant is 3 to
inverse.
6 minus 3, that is equals to 3, not equals to 0. So option P is correct, right? It has left in, it will have right inverse as well, right? That will work as a right inverse, right? Clear, na?
Sir, inverse, sir.
Oh,
Sir,
with in real
in,
entries.
yes, sir. This is not
No,
correct, sir.
no. Are you sure? Yeah, this
Because
is not correct. This is not
point
correct. This is
three.
not correct because determinant is 1 by 3. Yeah, one can check. This is not correct. Obviously, this is not correct. This is obviously not correct because 1 by 3 will be there, and when you find
Hmm.
the what is called this adjoint matrix, that will not always have one factor, right? A three
Sir,
factor will.
we can directly find inverse, sir.
Yeah, okay, let's find it. So determinant of, let's write it as, yeah, main point is that yes, this is 2 by 2 matrix, don't worry. So determinant of A is equals to 3, 3 to 6 minus 3. So that is not equals to 0, so there is inverse. But what is the inverse? So let's find B, that is equals to adjoint of A by the determinant of A. Now what is adjoint of A? Adjoint of A, just writing cofactor with uh, with reverse transpose. Okay, so that will be, let's write cofactor. Corresponding to first one will be plus. Second one will be corresponding to 3. Okay, I am writing directly. The 2, okay, corresponding to
Sir,
3,
2
corresponding to
minus
1,
1
3,
minus 3.
minus 3, minus 1, sorry, yeah, minus 1, 3, right? Right? This is correct, yeah. This is correct, na?
Yes, sir.
Actually, problem is that, yeah, I know this is very, for 2
There
by 2
is a
matrix,
minus 1.
you have to
Sir,
insert, yes.
this is a transpose of adjoint A, sir. This is.
Oh, I have not taken transpose, right? So 2 minus
No,
3,
no,
yeah.
sir. Sir, it is already, sir, transpose.
So this is na. So I have taken transpose that way because we have taken transpose because let's
Yes,
consider 3,
yes, sir.
that
Yes.
will be, yeah, 2, and let's
Hmm.
consider 1, that will be minus 3. That
Yes,
way.
sir. This is
Huh.
correct.
So this is the thing. So adjoint is this. So therefore one can, from here, because there is 1 and there is determinant is 3. So therefore B is equals to, will be 2 by 3 minus 1 by 3, 1. So that is not in the matrix with entries Z. Right. So option B is not correct. Option C,
Sir,
let it, yes,
sir, sir,
yes.
what is the condition that this inverse will belongs to this, sir? Entries will be, sir, from Z, sir. If we have given a matrix and it
Hmm.
has inverse, then what is the condition that the inverse entries of the inverse will be in Z, sir?
So for whenever the entry where you can look at entries of A is there, right? Even if you consider A is a matrix of big matrix and entries are all integer. So in that situation, also adjoint of A will be something for which entries are all integer. There is no doubt about that.
Yes,
But
sir.
only problem if there is the problem determinant A is not
Tell
one.
me.
If
Uh,
determinant is not one or minus one, then you have to. I think there. I don't have any idea right now how to then tackle. If determinant is one, you can directly go ahead one or minus one. You can directly
yes,
go
sir.
ahead. Okay, they are from integer. But
But the
when
question is this sufficient as well, sir?
yes,
Is this condition sufficient, sir?
yeah, sufficient, not necessary, no?
Ah, yes, sorry, sir. Necessary. This is not necessary.
Yeah, if determinant A is 1 or minus 1, in that situation,
Hmm.
integer entries, so all
Hmm.
the minors will be integer. Even even if the integers, if the matrix entries are of integer, and you are asked the question whether the B matrix B with not instead of integer, if they ask this is for rational, that will be true. Rational will be true, right?
Yes, sir.
And if it is written real, then I need here real. Because
Yes, sir.
in that situation, I mean, if the entries are real, so I mean that means one of them can be square root or something. Okay, not rational. Okay, so next question, it is saying that A B A matrix 3 1 1 2 with entries in Z Z6. So Z Z6, I'm writing it as 6Z
Yes.
is equals to 0 1 2 3 4 5, right? I'm not writing box. Actually, they are in general written as box. Then A be the matrix 3 1 1 2 entries. Then there is a matrix B with entries in Z6 Z mod Z6 6Z such that AB equals to identity. So I think let's similar process. Okay, but you have to, if there is 6, you have to do the thing. So 3 1 1 2. So therefore
Yes, sir.
determinant is 5. So there is no problem, right? Because it will be minus 1, but that is 5 again. I mean,
Hmm.
not
Yes.
minus 1, it will be 1 5 5 5. In this scale it is 5. Okay, now determinant is 5. So I think the same problem will happen. So adjoint of A is same 2 3 minus 1 minus 1. So I think same problem will be there, right? Adjoint, I need something. Adjoint of A, no, I
Yes, sir.
think
One will
this.
create problem, sir. One will create problem.
No, but I can write it as minus 1, right?
No, one. How can you write one, sir?
Minus 1 because 6 is 0.
One is not minus one, sir. In Z6. Sir, I am asking about one, sir.
Huh? No, no, no. Here, here minus 1 can be written 6 minus 0. That is the
No, no, no,
key.
sir. I am asking about one, sir. Only one, not minus. One is only one, na, sir.
Which one
Z6.
is 1?
One, sir. One. Sir, B you have written at 2 by 3 minus 1 by 3, 1. Those are 1
Oh,
in Z6.
no, no, this is correct. Huh?
Ah,
Adjoint
yes,
of,
sir, yes, sir, yes.
correct. Na? Minus 1
This is correct.
diagonal. Diagonal is multiplying minus 1 and sorry, diagonal is interchanging and cross diagonal will be minus 1. For
Hmm.
2 by 2 only, this scheme, not for other. Okay, so I can write this
Yes.
one as 2 minus 1, not in place of minus 1, I can write it as 6 minus 1, 5. Okay, this is, I can directly say that this is minus 1, right? I can write this
Yes,
one
sir.
is minus 1. This is minus 1 in Z mod
2,
Z6.
5.
So this is there, no? Then
Hmm.
adjoint A by determinant of A, that is there. Minus 2, 1, 1, minus 3. So I can write it as 2 minus 2 means this is 4. 1, 1, this is 2. Sorry, not
Sir,
2.
your adjoint is not correct, sir.
Why adjoint is not correct?
Okay,
Matrix
sir.
was
You
this one.
first. Okay, sir. Okay, sir. Okay, sir.
Correct, na?
हाँ sir.
Adjoint is correct. So I can write determinant of
Sir,
A. Yes.
This is
So,
correct.
if even if you have any doubt, so let's check this one whether this is correct or not. 4113,
Correct,
right?
sir. It is correct, sir. No doubt, sir. You can calculate,
12
sir.
plus 1, that is 13. 3 plus, this is 3, no? This is 3. 3 plus 3, 9, 6.
Zero. This will be
5.
zero.
So that will be 0.
Six, sir. This
So,
is six.
this one 6, no? 6. So otherwise it will problem, right?
Mm-hmm.
And 1 plus 6, 7. So this is 1001, right? Which
Correct.
is correct. So this is correct. So here you can look at, here is the option is only one option asked. So this will be correct. But let's go to the other option. Why the other option is not correct? If A is a real non-zero 3 by 3 diagonal matrix, then there is a real matrix B such that if A is real non-zero 3 by 3
This is
diagonal
correct.
matrix, this is correct, no? No,
Yes,
no,
sir.
no.
Why?
Real non-zero matrix. Matrix
Sir.
is non-zero. One diagonal can be zero, right? Let's take
But it
A
is
is
invertible,
equals
sir,
to
in that case.
1 0 0 0 0 0 0 0 1. This is diagonal matrix, non-zero matrix.
Non-zero 3 cross 3 diagonal matrix.
So I have taken 3 cross 3 diagonal matrix, no?
Sir, okay, sir. Okay. It should be. It cannot be, sir.
Yeah.
It may or may not be invertible, sir.
Yeah, it may or may not be invertible.
Yes, sir.
So this one is not correct. Only one question left from those collected because I don't have any other collection now. Okay, so I don't know what will be this answer. Let A be an n cross n matrix with complex entries. Okay, if n greater than equals to 4, which of the following statement is correct? It does not have any non-zero invariant subspace in
This is
Cn. That is false
false.
because you can always create a diagonal matrix for which non-zero invariant subspace will be there. Second option, that A has an invariant subspace in Cn of dimension n minus 3.
This is correct,
Why?
sir. Because A is a triangulable, sir.
Yes, that's true. Is this triangulable? Yes, and you know that for every, yeah, thanks to you, you ask that questions. For
Yes.
every dimension, you will have the invariant subspace.
Yes, sir.
Very good. This is very good. That as A is as the field of, okay, let me write it clearly. As the matrix is defined in complex field, matrix is defined over complex field, then for every k less than equals to n, that is why 4 is taken, because n minus 3 will be minimum 1. That's why. Understand? To confuse people, but
Yes, sir.
as well as make it correct. Okay. N minus 3, that is something random term, but why people may why taken n greater than equals to 4? But one can
Yes.
take n is 3, and here one can take n is here 2, n
Yes, sir.
minus 2. For every k less than equals to n, there
Sir.
exists a invariant subspace, invariant subspace of dimension, subspace of A of dimension k. So therefore, 2 is correct. Okay. So obviously all other will be false, but let's discard them because here is this is 1 mark question. Sorry, 3 mark question. So all eigenvalues of a real number. That's obviously not true.
Any skew Hermitian matrix will work for this.
This one will work also. There is I and minus I at the eigenvalue. A square does not have any invariant subspace in Cn of dimension n minus 1.
Not correct.
Not correct, but okay. A square does not have any invariant subspace of dimension n minus 1. So n minus 1 is less than n, or does not have any, sorry. Same reason. because here there it is, right? N minus 1 less than n, so less than
Because
equals
of
to,
this, sir, field, sir.
same argument, because n
Hmm.
minus 1 is less than n, right? Less than equals to n, so there will, and obviously positive, so therefore we will have an invariant subspace. Why a square will also have? Because a square is again a complex entry matrix.
Again, as a complex matrix, yes, sir.
So that's all. So this is all. I don't have any other now. So let's get back to the. So before this, I have to go little bit of orthogonal projection. So I think these all questions are from same paper. I mean, whatever I have quickly gone through and whatever it seems to me that can be done, whatever knowledge till now is there. So these are the problem. Okay. So orthogonal projection. I'll just quickly say something. Orthogonal projection. So what it says, let V be an inner product space. I'm writing short in IPS, and W be a subspace of V. Be a subspace. That means that is again an inner product space. And uh, now the question is, let beta is a vector in V. Then there is the main factor is that we have to find something such that we know whenever you have a vector space, inner product space, you have the idea of length. How, what is the idea of length? The that norm of v, a vector, is equals to inner product vv. And if I want to find the length between two vector, that is obviously this way one can give. Okay, this is the length of two vector. So we have the idea of length, and this is very interesting idea. Why? I mean, what inner product space and why length? Because length idea is why it is interesting. I mean, why people is going to study this inner product space and on talking about length. Maybe this is not connected to the what is called this linear algebra, but inner product space giving me length. Many things also give us length, but whenever you have the idea of length, you can say something positive or negative. You can say something whether something is positive or not, right? That length is positive or not. So then you can define the calculus, because the fundamental statement of calculus is epsilon delta, that is limit continuity, that for every epsilon greater than 0 there is a delta greater
Yes,
than
sir.
0.
Yes.
But you need to know when this delta greater than 0 or less than 0, we have to define this length concept in some vectors. Okay,
So there
that
is a matrix space now for this.
right, this is also again a matrix space, but this is something we have some extra properties in inner product space.
Yes. So you want to say that every inner product space, sir, gives a
The matrix
matrix,
space,
sir.
yes, that is
Yes.
clear, that d, this is the matrix. dvw is equals to norm of v minus w. You can check, it will satisfy. It will obviously the zero, it will be zero if and only v equals to
Yes,
w,
sir. Yes. All
and
proper.
interchange is there, and triangle inequality is there, that will help to show that triangle inequality matrix. Okay, so okay, what I just want to say, okay, so I just want to say there is a length concept. So let beta be a vector in v. So the question is that uh, we want to find a vector, we want to find a vector alpha in W, which is which is shortest to beta among all vectors in gamma, which is in shortest distance to, which is in shortest distance to W among all other vectors of W. That is, suppose I am taking a, suppose for example, let's consider 2 by 2. 2 by 2. This is R2, right? We know this is the R2 vector space. So suppose this is the So that is what I just want. That is norm of beta minus alpha that must be less than equals to norm of beta minus gamma for all gamma belongs to W. We just want to find, I mean, we are given a vector beta belongs to V. We want to find a vector alpha in W such that that will be shortest distance among all other vectors of W. That means if I take any vector from W, the distance from beta among all these distance, this alpha will be something for which the distance is shortest. Suppose W is the this R1 is the W, right? R1 means R cross 0. This is the W space, right? So now I have given a vector 2 comma 3, right? That will be 2 comma 3. That is something here. So now I want to find a position or vector in this R cross 0, which is shortest distance among all other, and we know what is that? That is the perpendicular, right? That is the perpendicular. And this is interestingly, you know that this from 2 comma 3 to what will be the shortest distance among all other distance. This is the what is the this is 2 comma 0 is the shortest one, shortest point of distance, and that is only one point. There will not be any other point. That means what I just want to say is that that is unique. You can't get multiple option there. Okay. So this is the shortest distance, that is the idea. So now what is the, I just one theorem is there, that is let V be an inner product space and W be a subspace of V with orthonormal basis. Orthonormal basis. Note that this is I'm writing orthonormal basis. Alpha 1, alpha 2, all the way alpha n. Okay, I have to write finite dimensional subspace. This is very important because this finite dimensional is the factor which is making this orthogonal projection. Okay, I have to write clearly. Be a finite dimensional subspace subspace of V. It's an orthonormal. This is an orthonormal basis of W. That means dimension is n. Then for any beta belongs to V, there exists a unique vector alpha in W such that norm of beta minus alpha is less than equals to norm of beta minus gamma. I mean, main question is that if I have a inner product space V and W is a subspace, whether can we always give this vector existence of this vector alpha, that always there will exist a vector alpha for any beta. We are given an arbitrary beta, and we are saying that we will always find a vector alpha such that norm of beta minus alpha will be less than equals to norm of beta minus gamma. That is not true. But if W is finite dimensional vector space, then we will always find a unique vector alpha such that norm of beta minus alpha less than equals to norm of beta minus gamma, and for all gamma belongs to W. And for this, we don't need orthonormal basis to give up to say this point. We don't need orthonormal basis, but to write this alpha, we need orthonormal basis, and that is summation of beta alpha I equals to 1 to n. Alpha I are orthonormal basis. Okay, so that's why you don't need to write below part. Okay, so this is called, then alpha is called orthogonal projection of alpha on W. And we have seen that, okay, sorry, I have writing alpha is again, no, sorry, beta. Orthogonal projection of beta of W on W. So that means for every vector, what we are claiming is that if W is finite dimensional vector space, then for every vector beta, for any beta belongs to V, we will always find a vector alpha. And what is that vector? This is the vector for which we will have this minimality of the distance from beta to a unique vector of W. So this vector is called the orthogonal projection, and that is denoted is by E. So denoted by E from V to W, and E of beta is equals to summation of I equals to k I equals to 1 to n beta alpha I alpha I. So this is the orthogonal projection. Okay, I think this is definition is enough. So let's go to the problem. What it says, give question says that given inner product space V is given an inner product space R3 with standard inner product and a subspace W that is spanned by 1, 1, minus 1 and beta is 10, 4, 5, then the shortest distance between beta and W. That is clear. You know the what is shortest distance. I have said this is the shortest distance. I mean, whenever you know two factor is there, here vector space V is there, here vector space V is there. Secondly, the finite dimensional subspace W is there. The finite dimensional subspace W is there. W is generated by this one, 1, 1, minus 1. So beta is there. We have to find the orthogonal projection and we have to find the, I have to find alpha and I have to find the norm of beta minus alpha. So let's do this. So here alpha is equals to, so clearly W is spanned by 1, 1, minus 1, right? This is the vector. So beta, there is the vector. So alpha, that is the orthogonal projection, is equals to ortho
9 by root 3, sir. 1, 1 minus 1.
9 by root 3. Root 3 will be there.
Sir.
Okay, so this
Because
is not, no, I need orthonormal vector, sorry. So this
हाँ,
is equals to, I have to find it orthonormal first. What
so
is the
root 3
orthonormal?
नहीं sir. Sir, we divide by norm square, na sir. So there will be 3 times, sir.
Yes,
3
norm
times
square,
1, 1 minus 1.
norm square, right. So 1 by root 3, comma 1 by root 3, comma minus 1 by root 3, right? And this is orthonormal basis.
No, sir.
Alpha by norm
No.
alpha. Alpha by
Norm
norm alpha.
alpha square. We sir divide by norm alpha square, I think.
No. Alpha by norm alpha is the orthonormal basis.
Okay.
Yes. Don't worry. Actually, if you look at from here, we will get 1 by root 3. From here, we will get 1 by root 3. That will go cancel out. That will give that root 3. 3. Okay, this is the basis. Orthogonal. This is the orthogonal vector. So orthogonal
Yes.
projection on W, that is equals to the 10, 4, 5 inner product 1 by root 3, 1 by root 3. So be careful. We have to take ortho normal. If we are not taking orthonormal, we have to do the, here we have to do the divide the fact things. But still we need orthogonal. I mean, suppose here we have only one vector. If we have multiple vector, in that situation, we at least need these are orthogonal basis. This alpha and alpha to
Yes.
alpha and at least need orthogonal basis. In that situation, I have to divide by norm of alpha square, not alpha, norm of alpha square. But if the vectors
Yes.
given is not orthogonal, you have to make them orthogonal by Gram-Schmidt orthogonalization process. And after that, you
Yes.
can do this step. Okay. So obviously in exam, I
Yes.
don't know for this exam, but even if it is come to the exam of the NET or any place where you have to use these things, so there they will not give you the orthonormal basis. You have to do, so 10 by root
Yes, sir.
3 plus 4 by root 3 minus 5 by root 3, that is 1 by root 3. I can do this, but I have to do this formally. So 10 plus 4,
So
6,
3 times
14, 9 by
1, 1
3.
minus 1.
9 by 3, 1, 1 minus 1. That's 2. So 3, 3 minus 3. So this is the alpha. So therefore, shortest distance is, therefore,
Norm beta minus alpha.
yes, shortest distance from beta to W is equals to norm of beta minus alpha, right? And what is that? That is beta minus alpha. What is beta minus 10, 4,
10,
5
4,
and 3,
5,
3. So 7, 1, 5 is there, 5 minus 3, that is 8. Norm of this vector.
8.
And that is equals to square root of 49 plus 1 plus
49, 1,
64, 50 plus
62,
64 root under 114.
10, 1, 1.
This is 1 not 1 1. 49, 50 plus 64. So all other option is incorrect. Obviously, there is no point of checking. Let's see second problem is similar or not. Second problem, V equals to R3 B inner product space with orthogonal is the orthogonal projection VW is the orthogonal. Okay, there you have to find. So the have to is some conceptual thing. So then I will go to a little bit of just only. So if E is an if V is a V is a inner product space. Inner product is writing is an inner product space. Is an inner product space and W subspace of V be a finite dimensional vector space and E from V to W be orthogonal projection, then E square is equals to E. We have this fact, and other thing is that I minus, this is first factor, I minus E is an or is not an is orthogonal projection. This is the only orthogonal is orthogonal projection on W path. But I didn't need what is the W path, that is the orthogonal complement. Okay, orthogonal complement, I don't know, I can't recall whether I said or not, but W path is equals to all those vector V belongs to vector space V such that inner product of V with W is equals to 0 for all W belongs to capital W. Note that this is the W path. For a subset, let W be a subset of V. In that situation, W path is equals to all those vector V in capital V for which inner product with V and W is equals to 0 and for all W belongs to capital W. Even W is not subset, still in that situation this is subspace. W path is subspace. Okay, if W is subspace, in that situation W path will be still be subspace, but yeah. So orthogonal projection on W path. So this is, here we have taken W as a finite dimensional vector space, vector subspace. So this is the orthogonal projection and this is the orthogonal projection. So therefore one can say here is that as for any orthogonal projection on a subspace, we have this factor. So this will be equals to again 1 minus this. This is a theorem I am not going to discuss. I am just going to use them. If you have any doubt, I can discuss. But if you don't have any doubt, I will not discuss. I mean that's theorem part. If you have, I mean, if you want that I should prove here, then I will. Otherwise, no. So here it is written that V from R3, V is an R3, and W is a subspace of V. Dimension is not specified, but E is given from V to W by E of X, Y, Z is equals to X plus Y by 2, X plus Y
Or
by
option
2.
B.
I think option B. I have to just check the option, correct option. I think option B will be, let's see, I have written for somewhere at the correct option. Option B. I hope so. Let's check. I'm not able to find it. One more. I will be able to find it. This is questions. This is B or C. Yeah. No. Option A is correct option. So let's see. Option A is correct option. So here, what is the question here? Is orthogonal projection on P and W? W par
Yes,
be the
sir.
orthogonal complement of W, then the orthogonal
The
projection
option
of
A is correct, sir.
option A is correct. So that is just clearly. Then,
I minus E. X by.
yeah, I minus E. Orthogonal projection of V on W par is I minus E. So what is the I minus E? That is equals to M. It is saying I minus M of X, M of X, Y, Z, that is equals to I minus E at X, Y, Z, that is equals to X, Y, Z minus this one given. I think I have written, no, both of them are plus, sorry, X plus Y by 2 Z. So clearly last option will be Z minus X plus Y by 2 y minus x plus y by 2 0. So this will be 2x minus y, x minus y by 2, y minus x by 2 0. So let's see which one is correct. X minus y by 2 minus x plus y. This is correct option. So obviously second one is not correct, third one is not correct, fourth one is not correct. So let's go to third problem. What it says, let so let V equals to R3 be the inner product space equal to the standard inner product and W be subspace of V. If E x y z is given
Option
by
D.
this way, option B,
D. D.
B. Okay, I
Option
think.
D.
I understand. You are saying this one, right? Yeah, this is correct option. So with the orthogonal projection of V, then the subspace of W with the subspace with the orthogonal projection of V on W, then the subspace W is what is the subspace it is asking. Okay, question I am not understanding. The inner product space equal to the standard inner product only W is subspace of V among EXI is given by this way. This is the orthogonal projection of V on W. The subspace W is what is the subspace W is it is asked. So EXI is given by this way.
Sir, we
So
can
I
find W
minus
per perp. W can be written as a W per perp.
right W part part
So,
right W subspace it is. So W can be written W part part. So W part is I have to find then W part first. W
uh,
part
W
okay
perp
I
is
minus
I minus
E
E.
is the orthogonal projection.
Uh,
That is in some pattern I think.
Sir,
That is
because
in
I
some pattern.
minus E is sir projection, so I minus EV in sir W. Actually, sir W is equal to sir W per piece I minus E V. V belongs to W.
Right, right. That is I minus V is equals to W per right. Right.
Where V
So then we
belongs to
can
W.
right. That's true. Not that I minus E V equals to W per. That's exactly correct. Exactly correct. Okay. That's exactly correct. So therefore, I can write it as x, y, z minus whatever this long thing is giving, 5x minus 2y minus z by 6, comma, minus x plus y minus z by 3, comma, minus x minus 2y plus 5z by then, okay, 5z 6, this term, whole into, this is I minus v. So then I minus e whole at x y z is equals to this. So therefore this is 6x minus 5x. So 6x minus all these things. So this will be x plus 2y minus plus z by 6. Other is this is 3y minus x. So minus x plus 2y minus z plus z. Oh, this will be plus x then. Okay, 3y minus this. So y plus z, but that's correct. 3. And third one is 6z minus, so plus x plus 2y, 6z plus z by 6. So therefore we have patterns that is x plus 2y plus z. If you take what we will have 1 by 6, 1 by 3, 1 by 6, right?
Yes, sir.
So so I have to write it a vector form. So 1 by 6 then I can common take x, y, z with this is vector of 1 to 1. 1 to 1 inner product by norm of n inner product is 1 to 1 that is 6. 6. So this is 1 to 1. Yeah, this is correct. So therefore this is equals to this is the case. So therefore I minus e is orthogonal projection on 1 to 1 space spanned by this, and that is equals to W path. Therefore, W equals to all those vector x, y, z in V such that inner product of x, y, z with 1 to 1 is 0. That is something all x, y, z in V such that x plus 2y plus z equals to 0. So also we can look at from here is also that this will be 0, this will be 0 if and only if x plus 2y plus z equals to 0, right? For all those x, y, z, for which this one equals to 0. As we know, I minus e is orthogonal projection on W path, for which the kernel is W, right? So kernel null space, not kernel, same thing, just null space of I minus e is equals to null space of I minus e is equals to W, right? So this is the case. So option D is correct. These are not correct. Okay, this is nothing special. This is just only, I think this is about checking that Vj finite dimensional inner product space alpha and alpha 2. Okay, let it alpha and alpha 2, alpha n be an orthogonal basis of V. Let T be a linear operator on V. A be the matrix of T in ordered basis beta, and which of the statement is correct. So we can know that if I
Sir,
take a
option A.
vector, yes, option A. That there is actually nothing. This is very this is normal statement, theorem statement. You can just check that T of, I mean I mean what is the RS entry? Okay, T of, let's write T of alpha S. That must be somehow T of alpha S whole R equals to 1 to n, right? This is the thing. T of alpha is R alpha. So what is the rth position element? So if you write, so corresponding to alpha s, you will have the column, s column, and corresponding to R, you will have R row. So there, that means R comma S entry will be T. Okay, no. Okay, I have to write it clearly. Sorry, I have
Sir,
to write
we
it clearly.
have to find the sir
With inner
image
product,
of
with using
image
inner
of sir
product.
alpha S.
Right,
Sir,
right. Image of alpha. That's true.
alpha S,
T
sir.
of alpha s. Let's write it
Ah.
as Ci alpha I equals to 1 to R. Right. So
Hmm.
now T of alpha s with inner product, if I do it inner product with alpha I, T of alpha s, if I do it inner product with alpha j, that is equals to summation of I equals to 1 to R Ci alpha I inner product with alpha j, and that will give only Cj, right?
Hmm.
But we know this is the entry of jth column, jth row, sth column, right? This is the entry of the matrix T with S comma jth row and S column, because we know corresponding to each element when we give a matrix representation of a linear operator T. So alpha 1 corresponding to whatever the coefficient matrix will be, that will give the first column. Alpha 2, that will give the second column. So alpha
Sir.
S will give S column, right?
Hmm.
So that way we'll get, so whatever the matrix representation it is given, let A be the matrix representation. So it's
S represents sir column, sir.
right. S represents columns and J represents the. So here it is R. So let's
Coefficient,
write. Right,
coordinate
right,
vector, sir.
right. So this is A J comma S. So therefore A R comma S is equals to T alpha S alpha J. I think this is there in Hoffman-Kuhn's book there it is. But main factor what you just keep pointing that it is orthonormal basis.
Sir,
If
alpha
it is
R, sir. Sir, there is alpha R, sir.
alpha, thanks. Alpha. So alpha. So this is the correct option, all other option automatically false, because this is matrix representation. It can't repeat unless if it is given that matrix is T is symmetric, skew symmetric, all these things. So we don't need to check anything because in symmetric there is a chance that it will repeat twice, right? Okay, so I mean multiple option can be correct because in that situation AR is equals to ASL. Okay, whatever point here users need to point out that orthonormal basis, because if it is not orthonormal basis, you can't write just like this way, right? Matrix representation will have, but T of alpha is, yeah, we need orthonormal basis. That's true. Otherwise, we can't make other element 0. We are making other element 0, na? Except J, we are making other element 0. That is possible because alpha, J are orthonormal. I can take orthogonal also, but no, orthonormal is needed because here we are getting alpha J square, right? So to avoid that one, we need orthonormal. Orthogonal is also not enough. Orthogonal is needed, even orthonormal is needed.
Sir,
Yes.
last option is also correct. I think
Oh,
NPTEL
last option is obviously correct. Sorry,
vector space.
I was thinking all are given in correct. No, 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 no. Last option is not correct. A
Sir,
R S. No, no, no. Look at A R S is equals to T of what it will be. T of alpha S alpha R, right? This is what, right?
huh,
Alpha R T alpha S. It will be only when it's, so that means this is
real.
equals to, I mean, this is real, right? Yeah, that's true. But it is
Yes,
saying
that
anything
that
about
is the
real?
point. No, no,
It
sir,
is
it is not saying. But I was saying that if it was real, then the option 4 will also
option
correct.
4 will be correct. Yeah, that exactly. If
Ah,
the matrix and all these things are given over the real field, then option 4 will be correct. But now it will be, as it is not there, so it is not necessarily correct. So therefore, this is not, because I have cutted it because there is the
ah,
only option, because it is written that the following
yes, sir.
statement is correct.
Right,
So
sir.
this was is a fourth. So let's go to. Oh, this is okay, what it says. What it says, let V vector space of R3 with inner product, standard inner product given. No, 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 not standard. This is different inner product it is given. And if fxyz equals to x plus 4y plus 2z, then the elements beta such that f alpha equals to inner product alpha beta is what? So if fxy equals to this, then the element of beta such that f alpha equals to alpha beta. Oh, so we have to find beta, right? So you can note that f of x, y, z is equals to x plus 4y plus 2z. Okay, here I think I should give an, okay, let me write them. It is, I should give a, I should give a theorem that is very interesting theorem. Some
Sir, last
theorem.
option.
I think first option will be, but that is not the point. You know that this will be 1 4 2 is the inner product thing, but we have to. But yeah,
Sir,
let me write it.
3, 2, 1 is there, sir. So I think, sir, sir, the option A
Uh,
is not correct, sir. I think.
Option is not correct. Okay, let's check. I write. Let's check. That is not a problem. If it is not correct, not correct. I'm writing the correct options only, but it is. This is problem. Option for last option is correct. You are saying, right?
Yes, sir.
I think it's correct. Let's check it. Okay. Then the element beta such that alpha equals to beta. Beta is finding. Beta is asking to find. Okay. So here the theorem that I just want to write, that is, let me write it. Let V be an finite dimensional inner product space. Inner product space with
Sir, you are right, sir. Option A is correct, sir.
option is correct. Okay.
Sir.
Orthonormal basis alpha
1 by
1
3 to 2 beta is equal to.
1 by 3 to 2.
Hmm.
Okay. Alpha 1 dot alpha n. This is the orthonormal basis of V. Then any linear functional is linear functional f on V is given by f of a vector x is equals to inner product x with b for some unique beta in V. Okay, yeah, this is the thing. It is saying that for any inner product, we should have some inner product because we are considering finite dimension inner product space, but this is true for only finite dimension. If we go,
Sir,
if
where
we
beta is given by, sir, summation f of alpha j conjugate into alpha j, where
right, alpha
uh,
j equals to 1 to n. Suppose then, yeah, suppose that's true. Suppose we have the vector x is a summation of xi is the coordinate corresponding to alpha and alpha to alpha n. Then this will be summation of xi beta I bar, that is equals to f of x. So in particularly, if you take alpha I, alpha j, then f of alpha j will be beta I bar, beta j bar. So beta j will be alpha j bar. That way you can find. I mean, if you know this one first, okay, forget about this. This is the correct. We don't need to write this one. Okay, so what it is said, let V be the R3 vector space equipped with the inner product given by this way: x y z x y x x1 y1 z1 equals to this. So let's write alpha equals to alpha 1, alpha 2, alpha 3. This is not a vector. This is in sorry. This is not an orthonormal. This is a vector, and beta is equals to beta 1, beta 2, beta 3. Right? That is again a vector in R3. Right? So now inner product we know this. Okay, this is also given. So f of alpha is equals to inner product with alpha beta. That is equals to, with this formula, it will be 3. Okay, I should write alpha equals to x1, x2, x3. Then it will be x y z. Then by this formula it will be 3x beta x1 x2. So x2 is beta 1 plus 2 y1, that is y, beta 2 beta 2 y2, that is beta 2. Okay, z1 z2 again. Okay, z1 z2. So beta 3. Oh, just only coefficient they have changed, nothing special. Sorry, why I'm just getting beta 3. This is the thing, and it is saying that x comma y comma 0, x comma, sorry, this is equals to, according to the formula, this is equals to x plus 4y plus 2z. Now we have to find beta 1, beta 2, beta 3, right? You can take alpha, that is equals to x comma y comma z, as 1 comma 0 comma 0, right? You can take this. So what you will get, you will get in the left hand side, you will get 3 beta 1, but you'll get the right hand side, that is 1. So that will give beta 1 is equals to 1 by 3. You can take alpha equals to 0 comma 1 comma 0, and that will give 2 beta 2 equals to 4. That will give beta 2 equals to 2, and alpha equals to, if you take 0 comma 0 comma 1, then you will get beta 3 directly, that is equals to right hand side 2. So beta 3 is equals to 2. So beta 1, beta 2, beta 3 is equals to 1 by 3 to 2. This is correct. So all other option is incorrect. Why all other option is incorrect? Because there exist
so unique.
unique,
This is
right?
unique.
Unique. So because why it is unique, you know the construction that this is, sorry,
No, sir,
the
because
it is the how it is constructed. F is a functional, f is a unique function. You know these are the fixed values. So f of alpha are fixed value. So coefficient is fixed. So what is the chance to be another vector? Because every vector has a unique coordinate corresponding to an ortho basis at least, right?
yes, sir.
Okay, so this is it. This is it. It says that A equals to written identity 1 1 identity is the matrix, and T matrix of T with respect to the standard order basis of the linear inner product space C2 with standard inner product defined on it. Then the adjoint operator T is okay. So basically, we have to give the again a theorem. Yeah, that's correct. So this is at matrix of adjoint of a linear operator. Matrix of adjoint of a linear operator. Okay. First of all, what is adjoint? That I just a little bit. What it says that for let V be a finite dimensional inner product space. Inner product space is required. Inner product space and T from V to V be a linear operator, right? Then there exists a linear operator T star from V to V, a new linear operator I am saying, unique linear operator T star from V to V such that T V W is equals to inner product V T star W. Okay, how this will happen? This is very interesting. That will go from this what is called uniqueness thing. Uniqueness thing. Why this uniqueness thing will have? Um, why this uniqueness? Okay, for we just want to find T star W, for example. So for any V, okay, for any fixed W in V, consider F from V to the field F by F of V is equals to inner product V, sorry, TV with W. This is a linear functional, right? Why this is linear? Because T is linear. So that's why F is linear. That means F of C V1 plus V2 is equals to, so why this is linear? F of C V1 plus V2 is equals to T of C V1 plus V2 inner product W. You have to use the linearity of T. You will get C T V1 plus V2 with T V2 with W. Okay, so T V2 with W, then you will get it as C will be outside. This is coming via the properties of the inner product T V2 W. Then C of F V1, sorry, yeah, C of F V1 plus F V2. So F is a linear functional, but we have said our theorem is that for every linear functional there exists a unique vector beta for which it is inner product, right? So therefore there exists a unique vector beta star belongs to the vector space V such that f of V is equals to V inner product beta star, and define an operator T star from V to V by T of beta is equals to beta star. Okay, T star of beta is equals to beta star. Then you can check this is linear operator and all this thing is there, and ultimately no, this is conjugate linear, I think. T star, why is it conjugate linear? No, this is linear. This is linear. This is linear. Linear operator, define T star by this way. This is a, one can check, this is linear operator. This is a linear operator. Linear operator. This is this interesting fact that for every linear functional, there exists a unique vector beta with whom we can take the inner product and get all the linear functional. That means what it is saying is that we have all the linear functional here. What is the all linear functional collection? That is all vector beta in V. Corresponding to all vector beta in V, we can give a linear functional f from V to V by f of alpha is equal to inner product alpha V. That means you can say that here corresponding to, I mean, if you have a vector space V and we consider inner product space V and consider V star. What is V star? V star is the dual space of all linear functional. Then there is just a correct correspondence from V to V star. And what is that? Beta going to the linear functional f beta, which maps alpha to inner product alpha beta. Okay, so that's why V and V star is same dimension. But here it is always I'm taking V is finite dimensional vector space. V, if V is infinite dimensional vector space, then it is not true for always. But when V is an inner product, V is in Hilbert space, in that situation this is also true for all. What is Hilbert space? That obviously not in your syllabus, but obviously you'll encounter in masters. That this is true also. I mean, every time I am saying that this is true for every finite dimensional vector space. But if we even remove the finite dimensional vector space, then when this is true for an inner product space, now when the inner product space is also a Hilbert space, there is some definition of what is called Hilbert space and all these things. But there is also the same correspondence that corresponding to every vector V in V, we will get a linear functional FV which is map inner product X V, that way. Okay. So there is also you can define the adjoint, because this adjoint is possible to define because we have the uniqueness of the linear functional and the way we are defining. Okay. So this is a linear operator. So now the matrix. So theorem is that let T from V to V be a linear operator on a finite dimensional inner product space V. Let alpha 1, alpha 2, alpha n be an orthonormal basis of V. Then this is an orthonormal basis of V. Then if A equals to Aij, n by n matrix, be the matrix representation of T with respect to the orthonormal basis alpha 1, alpha 2, all the way alpha n, then A star, that is adjoint and transpose, that is equals to adjoint and transpose. This is adjoint means bar and transpose, that is adjoint, is the matrix representation of T with respect to T star, with respect to this orthonormal, same orthonormal basis. Okay, so let's go to the problem and take the adjoint and finish this problem. There is nothing, this is the theory. What it says, let V be finite dimensional inner product space of dimension n. V is an order basis of V and G equals to G J K. Okay, J is row and K is column, but G J K equals to alpha K alpha G. So that means, okay, I was this problem or another problem? That's true. I was not this problem. This
Yes.
is the problem. Yeah, this is the problem. Yeah, that one is also easy. Don't worry, we will go there. So this is the problem. But it says that A is equals to identity. Okay, 1 1 identity. So this is the matrix representation of T. Is the matrix representation of T is the matrix representation of T with respect to standard ordered basis. That is 1 0 0 0 1 0, that one. Okay. So 1 0 0 1, that is whose standard order basis inner product defined on it with standard inner product, that is summation of xi y j bar xi y I bar. Then the adjoint of T star, then matrix representation of T star with respect to the standard ordered basis. Standard ordered basis is just adjoint, that is bar I bar 1 1 I bar, and at transpose is it's this is same. So I bar is minus I 1 1 minus I. This is the matrix representation. Now it is asked to standard order basis, then xy. You have to find xy. So T star xy is equals to minus I 1 1 minus I x and y is equals to minus ix plus y x minus y. This one. Let's see which one is correct. Okay. Here everything is, so I have to take common minus I. If I take common x minus iy, because we know that x plus iy, x plus iy, because minus I square is 1. That's right. X minus iy.
Sir,
So
this is only, sir. The matrix is, sir, corresponding to, sir, the
standard order basis.
T star. Yes, sir.
Yeah. So you once you said na that when you have standard order basis, then you can replace a transpose. That's true. But when you don't have standard order basis, then you can do replace a transpose. But you have to write vector x with respect to the order basis given. You can't write in that place the order basis of the standard order basis. Suppose you have given a fixed order basis alpha 1, alpha 2, alpha n, and now you want to, and you have given a matrix representation of T with respect to that order basis, right? Now if you want to write some vector, so you have to first take the matrix representation of a vector with respect to that new basis, which will be a column vector, and you can multiply with the matrix. Then that will be the correct coordinate of the vector. And after that, you have to change it to the summation of xi, that way. Okay. So this is the what it says. V be a finite dimensional vector product space. B is an ordered basis of V. G equals to this and this. So one can directly say what it is written. Interestingly, it is saying that V is a finite dimensional inner product space of dimension n. Beta is an order basis of V. We don't know what is the order basis. G equals to GJK, and GJK equals to alpha K alpha J, of which, okay, so yeah, they must say that alpha 1 alpha 2 alpha n is orthonormal basis, ordered basis. कुछ तो बोलना चाहिए. V is an finite dimensional inner product space of dimension n. If beta is an order basis of V and G equals to this, where Gj equals to this, then which of the following is or are correct? Incorrect. Sorry,
Are
not correct.
incorrect.
Huh. Okay, so we can take beta is in whatever basis I can take, right? So incorrect means they can't be correct. Okay, which are incorrect? Here alpha 1 alpha 2 is in basis, that's true. I don't know whether they are saying it orthonormal basis or not. Okay, G be the G be the matrix representation corresponding to that basis, right? Alpha 1 alpha 2 alpha n, right? So in that situation, GJK is equals to this is written. So therefore GJK is written this way. Yeah, it seems to that many things, these first three things are correct, so this will be incorrect. But let me first figure it out. I mean, the correct statement. I mean, there it is. Obviously, wrong thing is there because what it is, alpha k alpha j is not mentioned. What it is, it is not
Not
mentioned. What
conclude that the G is sorry, the basis is orthonormal basis, sir, or orthogonal basis, sir.
why
Because
that will be?
because then we can write the coefficients as, sir,
That we can
in the.
write, but why that will be necessary? He,
Sir,
for
I am
example,
asking that I am. This
ha, ha, ha.
cannot be the always the case, na, sir.
Yes, but that's what
Yes,
I'm
sir.
saying. But here it is also not said what is the alpha 1, alpha 2, alpha k. That is also not said. And B is an ordered basis. Beta is an ordered basis of B is an ordered basis of B. Okay.
Yes, sir. Yes, sir. Yes, sir.
So
Question is
ordered
incomplete.
basis of B, I can do the Gram-Smith orthogonalization. I can do the um, after that we can do the orthonormalization. That is not
But
the
we do
point,
not know alpha k, alpha j.
right? So I and also it is written that ordered basis. Even they have written that orthonormal basis. Still, I can take that alpha and alpha to alpha n as the orthonormal basis. So if we assume alpha and alpha to alpha n are orthonormal basis, then it is clear that rank of G is n because in that situation matrix will be identity. We can look at because all that situation it is the identity matrix, right?
Yes, sir.
Yeah, the matrix is identity because even no, if basis is not orthogonal, we can't write. Even basis is not orthonormal, still we can't write. This is let I'm taking let alpha 1, alpha 2 all the way alpha n is orthonormal basis. In that situation, then G is equals to obviously identity, right? G is obviously identity. कुछ तो बोल रहा है let T of alpha k that will be summation of okay okay. T of alpha k that will be summation of Ci alpha I equals to 1 to n. So T of alpha k inner product with alpha j that will give the alpha j that will give the G J K entry, right? And what is that? That is equals to given that alpha k alpha j. This is true for every alpha j, right? For fixed k, okay. I have taken alpha and alpha to alpha in any order basis, only ordered basis. I have not taken anything else. Then P of alpha k can be written summation of I equals to 1 to n Ci alpha I. So in that situation, Gjk, which is T of alpha k, is equals to, it is given that alpha k alpha j, right? For all j equals to 1 to n. That implies that T of alpha k is equals to alpha k. Why this is? Because why this is true? Because if this is true for every alpha j, for any x which is equals to summation of some some t I alpha I equals to 1 to n, take an vector right this way, right? So then what we'll get? Then we'll get t of alpha k
Sir,
inner product x, yes,
sir. If
Yes,
we assume this equality
hmm.
and put the right hand side into left hand side, sir, then we get, sir, inner product T alpha k minus alpha k comma alpha j, sir.
That's true. That's true. Yeah, that is what I'm basically, essentially, that is what I'm doing. Yeah, that is what I'm doing. Uh, yes, that is what I'm doing. Don't worry. That is what. So basically, what I just want to say is that you will have T of alpha k inner product x. I have taken. Okay, let's take arbitrary vector x. Okay, I know this problem may be wrong. So we have time. So let's do some play. Okay. So we have taken an vector x in V because every vector x in V is some linear combination of bases because we know that alpha and alpha to alpha in basis. So T of alpha k with inner product x, that will be I equals to 1 to n Ti alpha, right? So then I can write it as T of alpha k with summation of I equals to, okay, summation can be taken outside and Ti or complex, I can take Ti complex number. So summation of Ti bar inner product T of alpha k with alpha I, right? I equals to 1 to n. So then I can write it as I equals to 1 to n T of I bar. I can write it as inner product of alpha k with alpha I because this is what we know. This is given. Okay. So that means I can take them inside and write it as x. So the main point is that this is the point is that T of alpha k inner product with x is equals to alpha k inner product with x for all x in the vector space V. Right. So then this is the property that says that T of alpha k is equals to alpha k. Why? Because T of alpha k minus alpha k inner
Sir,
product with
if inner product of
with
x comma y is equal to,
0.
no,
Yeah,
no,
that's true. This is
if,
this is what.
sir,
This
if
is what.
inner
So
product of, sir, x comma w is equal to y
inner
comma
product x equals to
for
0,
all
na.
w, sir,
So
for
in
all x,
particular, yeah, in for all x belongs to vector space V. In particular, whenever x is equals to T of alpha k minus alpha k, then norm of T alpha k minus alpha k is equals to 0, and that will give T of alpha k equals to alpha k for all k equals to 1 to n, because we have taken fixed but arbitrary, right? We have taken fixed, but ultimately we have shown that, for example, that implies T is equals to identity operator, right? So I'm writing this is in statement. Therefore, T is an identity operator. T is identity operator. Oh, so then question is not wrong. If we just take that, this is a basis. I am not taking orthonormal orthogonal because I have just used the fact that what is the this matrix representation of GJK, right? So that means T is identity operator. So as T is identity operator, rank of G is n, G is diagonalizable, G is Hermitian. That's true because identity matrix representation with respect to any basis. So therefore, as a option of this question, correct option is the last one because G is singular, that is false because G is identity. So that's why this is non-singular, that is invertible. Clear?
sir, you have taken, sir, alpha is, sir, the orthonormal basis of this vector space,
No,
right?
no, no. I have not said any places. No, no. I don't need this fact anymore. I don't need this fact. If it is orthonormal, I don't need to go anything. I have not taken orthonormal basis. What I have taken is that suppose we are giving a basis, order basis, right? This is the order basis we are giving.
Sir, EJ, sir, you have written inner product T alpha get alpha j. This is
Hmm.
only true now when you assume that the alpha k I are, sir, orthonormal basis.
That is.
Yes, sir, you have proved, na, sir, in previous question
I understand.
by
Understand.
assuming that. Yes, sir.
Right, 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 right. So T of
I
alpha
think, sir,
j.
the question is in the question is
No, no. Question may be wrong. That I understand, but I
yes,
just
sir.
want to say, suppose T is there, matrix representation is there. What is the entry of? No, I have not taken. I have correct what I'm saying. I don't know what is the. Let's tease an operator, right? Right?
Yes, sir.
Now, and we have a basis. We have basis alpha and alpha to alpha. Now I have taken T of alpha 1. I can write it as something linear combination of alpha j equals to 1 to n, right? What is the matrix representation with respect to this ordered basis? That is, when we take inner product with alpha I, right? Then that will be I comma j entry, I comma j entry of the matrix.
Yes,
That
sir.
okay, that
Why-
will be the I comma j entry of the matrix.
Sir.
And I don't know whether what is 0 or not. I don't know. Okay, I have just taken that this is given that I comma j comma k entry is given that alpha k comma alpha j.
Sir,
It is
but
given.
how are you replacing, sir, the sir alpha k as T alpha k, sir?
No, no, no. I am
Because
not replacing alpha k t alpha k.
sir, how you written T alpha k alpha j is equal to G j k? Because G j k is given, sir, alpha k alpha j.
Got it. Got it. Got it. Correct. You are correct. This is true only when orthogonal basis.
Yes, sir.
Orthogonal basis. That is right. That is what I just want to. I said there. That's true. That's true. So all these things is complete nonsense then. Because we have to take orthonormal basis, otherwise I don't think, because there is no other no other way. So let orthonormal basis, and option is that last option. So this is just even orthonormal is not correct. Orthogonal is not going to work. I have to take orthonormal. So let this is an orthonormal basis.
Sir, you should have written, sir, in if B is an, sir,
Hmm?
orthonormal ordered basis of B, sir. The
Right, right.
question.
That question, yeah, that is the problem. I understand that. If it is written that with an ordered basis, still that is okay. That we can assume that alpha and alpha 2 was that one. Okay, let it to 9. What it is. Okay. So what the 9 problem says that let Txy is given by this way. Linear operator inner product space equal to the standard inner product. Okay, this is very easy. T star denotes the adjoint of T. Then T, what is the T star? So matrix representation of T with respect to standard order basis. Matrix representation of T with respect to the standard order basis is A equals to 2, 3, 1, 4, minus 1, 3, 5, 2, minus 1. Because if you take 1, 0, 0, you will get 2, 4, 5. That way. Okay, 2, 3, 1, 4, minus 1, 3, 5, 2, 1. 5, 2, minus 1. So therefore, the A star is equals to 2, 3, 1, 4, minus 1, 3, 5, 2, minus 1. This is nothing but matrix representation. The same problem here. Right, right, right. Oh, has been discussed by another. This is the same problem. Okay. But all problems are same, I think, no? Because we are said to do this. That's why I have tried to. Problem is that to create problem, that is a problem. We have to find problems and all these things, and there is option net. We can take from there, but that will be, yeah. Actually, I don't have time. Yeah, I actually, that's the problem. Matrix representation of A, matrix representation of T with respect to the T star adjoint with respect to the standard order basis. Last time when I was there, yeah, I can take problem. That is true, but that I have to first find. Actually, you know that I am not appearing any competitive exam now, so that's why question are not in my hand. I have to find question someplace. That is the problem. Yeah, still that 4 questions I have found, and even 12 minutes I take time and found that questions and done. Okay, you can send me. You know my mail. You can just send me. I'll try to then do those problems. Okay, so here is the 152 is the uh, vector. We have to just do this 3 1 2 1 3. The last time when I was TA of a course, that time only I was TA, so that's why problems are not repeating. But this time, as the batch is, it seems to be batch is the very large, so that's why they are giving 2 TA. Okay, so 5 10, sorry, 2 plus 20 22 minus 10 12, 3 minus 5 minus 2 minus 4 minus 7, 1 15 16 plus 2 18. What it is? No, I have made some mistake. Okay, 3 minus 5 minus 2. What is the mistake I have done?
So minus 6 is there, sir.
Here it is minus 6.
Ah.
But 3 minus 5 minus 2. Oh, minus 6. That's true. 1, 3, 5, 15. 15 plus 2, 8, 30, 17. Yeah, what I have done. Okay, this is the one. So minus 6, 17 or 18. That was correct, I think. 5, 6, no, that was 18. That was 18. That was 18.
So 3 minus 5 minus 4, sir.
3 minus.
5 minus
No, no,
4.
no.
So that will be minus 6.
Oh, no, no, that is correct. 3 minus 5 minus 12, that is 6. That's the next one I'm just talking about. Next one is 18. So 3, 12 minus 6, 18. This is the correct one. So other option are incorrect. So I think there is only one option. This is all, and this is also theory. Let's do. So if U is the, okay, there is the one theorem is there. So let's write it. I have at that time if let uh, let V T from V to, sorry, W be a W subspace of V be a subspace, finite dimensional subspace, finite dimensional subspace of an inner product space V, and E from V to W be the orthogonal projection, then we know that E square equals to E, that is idempotent, but as well as E star E equals to E. Any orthogonal projection is self-adjoint. This is called self-adjoint. So there is a very interesting. So we will use this property. So let's start from the last one. Okay, last one. Check. I have to check. Inner product question is these are correct. Alpha beta. I can write it as E alpha plus alpha 1 minus E alpha. I can write this way with inner product E beta plus I minus E beta. Okay, one thing I just want to say here is that here E from V to W be orthogonal projection, that implies W parp is equals to the null space of E. Similarly, I minus E from V to W parp is orthogonal projection, and similarly W is equals to null space of I minus E. Okay, and any vector can be written as for any alpha belongs to V, alpha can be written as E alpha plus I minus E alpha. I can write this way. alpha equals to E alpha plus I minus E alpha. So note that E alpha is obviously contained in W and this is contained in W path, right? So that means every element can be written this way, and interestingly this is the unique decomposition. Okay, so therefore, and also we know that W and W par are orthogonal to each other. So therefore, this vector with this vector is orthogonal. This vector with this vector is orthogonal. So therefore, whatever is remains, that is this with this, and this with this. All other product, you know, the product means like A plus B into C plus D. A C B D A B D C, all thing will be there. But here, all other entries are becoming zero. So therefore, it will be E alpha with E beta. This one will stay there, and yeah, this is correct. I minus E alpha, I minus E beta, this is there. So that means the last option is correct, and as I have said is self adjoint, so E alpha beta, that must be equals to alpha E star beta, because we know by definition of T adjoint, if it is exist, then T alpha beta equals to alpha T star beta. So here it is. So so this one equals to this, but also we know that alpha E is self adjoint, so this is the one. So but also we know that E is idempotent, so I can multiply E square, E equals to E square. E is idempotent, that means E square equals to E.
Yes, sir.
Huh. So E
Correct.
square beta, but E cube beta, can I think, yeah, I can multiply, no? E square is equals to E.
Ah, sir. E cube beta.
So again multiply
E
E
cube.
cube equals to E
Sir, e
square.
to the power n e for all
Yeah,
n.
right. That's true. E to the power n equals to. So I can, okay, I can. So let's write it as in next to E cube beta. So therefore, this option is correct. Similarly, third option is correct. First option is second option is correct. E to the power alpha beta. We know that I minus alpha is orthogonal projection on W part. So therefore, this will be alpha with I minus E.
Sir,
Yes,
basically you want to say that, sir, every projection operator is, sir, self-adjoint.
every
Or you can say every idempotent operator is self-adjoint.
on an inner
Sir,
product
every
space.
idempotent operator
On an inner product space,
is self.
because idempotent operator need not be on the uh, idempotent operator need not be on inner, I mean, operator need not be always on inner product space, but yeah, self edge, okay, that's true, because without inner product space we can't say about the self adjointness, right? Whenever you are in finite dimensional vector space, in that situation only. If it is infinite dimensional,
Yes.
I don't think you can say self adjointness. Infinite dimensional, it is not true. Even inner product space, infinite dimensional
Okay.
inner product space, their idempotent operator is not necessarily self-adjoint. I think there is an example
Okay, sir.
now. Okay, so this is the thing. This is the thing, because I minus is self-adjoint, so this will be alpha I minus E beta. So therefore, option C is correct and option B is correct, and option one will be false. Let's write I minus E whole alpha with beta. This can be written as alpha with inner product beta minus E alpha with inner product beta, right? But this can be written as alpha inner product beta minus alpha E beta. So that is obviously not always this one, right? Not always. It can be if alpha and beta are orthogonal. This is not always true. I can write it as not always true. Okay. I mean, this one is not always true. Not equal to is also not always true. Equals to is also not always true. This one is not always true. Because if alpha inner product beta is 0, then it will be equal. If not equal, not 0, then it will be not equal. This is, so therefore this option is not correct. So this is all. I think time is there. So you know my mail ID. You can send me. You can collect linear algebra problem and send me. I'll assure you, at least I'll try to do 1 hour, because I have to do at least some of the problem here, because if someone check this video from the from the main team of this course. They can ask me why you are just teaching just teaching the what is called the net questions. So that's why I have to do at least 4 or 5 questions. But I'll try to, if I have collection of questions which are covering all these materials, whatever we have discussed or done in this course, then obviously I will try to solve those problems. At least one
Sir,
hour.
this is sir advanced. Sir. This is advanced linear algebra course. Now you can sir discuss anything, sir. It's
Yeah,
not
that's
sir
true.
basic.
That's true. That's true. That is
Yes,
true.
sir.
Okay, so
Advanced means sir, you can cover anything, sir.
yeah, I understand that should cover anything because you are going to in this what is called inner product space. So obviously there is. I don't know. I don't think in course there is the what is called the quadratic form. I don't think because there will be
Yes,
two with
sir,
there
there is sir. By
there is
linear
in
form and quadratic forms.
oh
Yes, sir.
linear form is there. So that means quadratic form is there.
Yes, sir.
Okay, so then quadratics we can do some. I think there is two more tutorial is there, but one will be extended. So three this tutorial is there in total. So we can discuss at least 1 hour.
Sir,
And
sir,
if you
kindly share your sir, email ID, sir.
my email ID, you can yeah I'm writing here. You can just copy from here. MA21D018 this mail dot yeah, this is the mail ID. Uh, okay. So just send at least 2 3 days ago because you know those are net problem. I have to take time then. Okay. So I'll try to discuss, just collect and send. I will also from my also at least try to 4 5 questions as we discussed today. At least 4 5 questions I'll try to collect. Okay. So if there is no doubts, then we can stop here, right?